brackets. Grab this guy, get rid of that, go over here. Let's see, where's my bookmarks? Here we go. Here, whoops, sorry. I'm going to find, my phone's buzzing. I'm going to find, now wait, how would I, do you remember where we talked about how could we do this? Because my chart only gives me values to the left, but because of the symmetric property of the normal curve, Z alpha over 2 on the left is exactly the same. It's going to produce 0.025 over here and 0.025 on the right. So let's find 0.025 on the left, and then we can just make it positive. So we'll just make it a plus or minus, right? So 0.025, 0.0256, hey, look at that. Boom, I got it perfectly. And that is, if I go on this row, negative 1.96. So let's stumble back to this guy. That just told me that Z alpha over 2 is, what, plus or minus 1.96. All right? I guess technically I should write Z alpha over 2 equals 1.96 and negative Z alpha over 2 equals negative 1.96, right? But hopefully we get what's going on. All right, now let's make this guy big again so we can build one of these out because they're fun. All right, now all we have to do is this. We got P hat. We got Q hat. So my confidence interval, my 95% confidence interval is going to be 0.8 minus 1.96, that's this guy right here, times the square root of 0.8 times 0.2. Wow, my 8 doesn't look so good, does it? Divided by 5,000. Ooh, that's going to be pretty small, isn't it? That's the left-hand side of my interval. The right-hand side is going to be 0.8 plus 1.96 times the square root of 0.8 times 0.2 divided by 5,000. All right, now I'm good, but I'm not that good. So let's go on. I'm going to go 0.8 minus 1.96, second square root 0.8 times 0.2 divided by 5,000. And I'm going to end my paren, and this thing is going to be on the left. It's going to be 0.789. So let's go let's write the whole thing, 0.789 on the left, and then I use my second entry on my calculator, and I'm going to turn it into a plus, and I'm going to get 0.811, which I could figure out if you think about that. Since error is the same value, whatever I subtracted from 0.8 to get to 0.789 is the exact same term that I'm going to add to 0.8 to get to 0.811, which is what, about 11 thousandths, excuse me. Ta-da! That is my 95% confidence interval. All right? We are 95% confident that we produced an interval that if we repeated this process many, many times, that 95% of those intervals would contain the true population. And at this point, hopefully you're starting to figure this out. You guys, statistics is lawyer math. It's a wing and a prayer. At this point, we are hoping that P lives somewhere in here. But we don't know. Maybe P, I mean, it's highly improbable because N is huge. That's a big number of people. All right? Hell, I just said hell. I apologize if you're sensitive to horrible curse words such as hell. I meant Hades. Let's say that the P is actually 0.65. Oh my gosh. We went horribly wrong, didn't we? However, we can only go based on what we have. There may be all kinds of bias in the way in which we ask these 5,000 people these questions. You know, if we went to Dog Park, Oregon, and asked how many, went to door to door asking people, chances are my proportion is going to be a little bit high. Okay, hope you enjoyed that. That is not only the theoretical foundation, the mathematical foundation for where the formula came from. Again, I always hated it when teachers just said, here's the formula, shut up and use it. And unfortunately, your textbook does that, but it's okay. It's an introductory course, but I figured you guys would want to see it. All right, enjoy. All right, so I've redrawn my confidence interval formula here for just a sec. Now, let's look at something. if we do, sorry, I have to take these big breaths, because this is where we start getting kind of crazy theoretical, and I don't want to lose you guys. So you can always write questions down and bring them to class if you're having a little bit of confusion on these, because I realize you may not get it first pass through. You may have to watch it a couple times. Let's look at what's going on here. Let's go back to the confidence interval that we built here. All right? This is a relatively small confidence interval. We're off by 1.1%. That's our margin of error. Our margin of error is 1.1% because we're 1.1% above 0.8 and 1.1% below 0.8, right? Does that make sense? Now, why is that so small? Because 0.8 and 0.2 are what they are. You go out, you run a poll, and you get these numbers. So these guys are locked in. This guy is locked in, right? Because I said it's a 95% confidence interval. For all 95% confidence intervals, this will always be z sub alpha over 2. So really, if you think about it, if the thing that dictates the size of the confidence interval the most is n, it's this guy. It's how many samples that you want to take, okay? So if we stumble over this away, let's say, for example, let's say that I'm going to have a 95% confidence interval, and I want my margin of error. I want my margin of error. Sometimes you'll see this as MOE. You'll see it on the, they'll always do it in really small type when you hear statistics on, or when you see a statistic on a television show or written into an article of some sort. Let's say that I want my margin of error to be plus or minus 3%. Which we know is plus or minus 0.03, right? I'm going to have a 95% confidence interval, right? Now, here's what I want. Let's assume that we're still talking about the dog problem. Okay, we already ran a little initial study that gave us that our p-hat was known, right? And we know that that's 0.8. So we did an initial study. But I'm going to build a 95% confidence interval, but maybe I don't want my error to be so small. I want it to be a little larger. I want to be a little looser with this. And I know that my q-hat is 0.2. Now, think about this for just a sec. Remember, my error term is this, right? If I let error equal z sub alpha over 2 times the square root of p-hat q-hat over n, and n dictates the size of my error most strongly. I could change it if I was talking about a 95% confidence interval versus a 99% confidence interval, this number would change. But n really tells me, it's really going to dictate how big or how small my error is. All right, so in this case, what we have is a problem where we went out and did some initial research, but I'm told, hey, I only want a 3% error, 3% margin of error. Well, watch, I can solve for n. Remember, the square root of a quotient is the quotient of the square roots. So if I simply cross multiply by root n, I get root n equals z alpha over 2 times the square root of p hat q hat over error. So n is equal to z alpha over 2 over error. Now watch what I'm going to do here. It's nothing too fancy. Remember, I'm just going to square both sides times p hat q hat. You see what I did there? I just squared both sides. So if I want, look at this. This is a formula that can tell me exactly how many respondents I need to go out and gather if I want to be within a certain margin of error. Excuse me. So we know, watch, check this out. We know that z alpha over 2 for a 95% confidence interval is 1.96. I know that my error is 0.03, so I'm going to divide by 0.03. And then I'm going to square that, and I'm going to multiply times 0.8 times 0.2. Let's see what we get. Now, before we do that, think about this. What's your guess? Do you think if I'm going to be 3% margin of error, is n going to be smaller or bigger than 5,000? Remember before n was 5,000. Is it going to be bigger or smaller? And let's see, I'm going to work it out on my calculator right now, okay? So I'm going to go paren 1.96 divided by 0.03, and I'm going to square that, and I'm going to multiply that times 0.8 and times 0.2, and off I go. Hey, look at that. It's considerably smaller. 682.95, 682.95. So to make sure that we're within that, we're going to end up with 683. All right? So when I go out and I want to be within a 3% margin of error, N only doesn't have to be 5,000. It can be 683. Look, if I stumble back here again, remember when N was 5,000? I got a 1.1% margin of error, considerably smaller, much smaller, because as this number grew, the interval got smaller and smaller. Okay? Now, this kind of a problem right here, this is where prior research is done. Notice I had to go out and do a little research first. What if no prior research is done? Well, again, you're going to refer to statistics as lawyer math a few times, and this is going to be an example where you're like, well, this sounds a little crazy, and you're not wrong. If no prior research is done, we are going to simply assume that p hat equals 0.5 and q hat equals 0.5. Now, you may say, well, Ripley, that's absurd. That's crazy. 50% of American households owning dogs, or let's say that 50% of American households have 3 or more cars. Well, you're right. That's absurd to think that. So if you think it's that absurd, as a researcher, think about this. This is a tool of research. If you think that that's wrong, go do some prior research. Do a real simple, 100, 200, 300 sample size proportion and get after it. That will give you these initial values that you can play with. Because this really is, I'm not going to lie to you, this is the swinging of a piñata stick. You're saying, well, all things being equal, I guess all things are equal, and therefore P and Q, the number of respondents that do have a dog versus the number of respondents that don't have a dog, are equal. In other words, if my hands are tied, we just assume that they balance out at 50-50. But we end up with the same formula. It's just instead of P hat and Q hat being 0.8 and 0.2 or 0.7 and 0.3, who cares? It's simply going to be 0.5 and 0.5. So you'll see this formula written as N equals Z alpha over 2 over R squared times 0.5 squared, or Z alpha over 2 over R squared times 0.25. Okay? All right, we're going to have a lot of fun with these. We're going to mess around. I think you'll find it pretty interesting how you can use confidence intervals, and they're really, really powerful with hypothesis testing, which, of course, we're going to get into as well. All right, I hope you enjoyed the section, and we'll see you in the next little lecture. Bye-bye.